Good morning, welcome to new lecture. In this lecture I will talk about stiffness of one member, of course, axial stiffness, to see what is the axial stiffness, and if we calculate axial stiffness of the member, it will help us to solve a lot of problems. But we need some assumption, so let's look at that assumption and I will refresh your memory. The first things I would like to talk about that it is Hooke's law. As I mentioned, Hooke's law mentions F is equal to Kx. What does that mean? For linear elastic material, force and deformation, it is proportional. It means if we have one spring and I apply force, displacement or deformation and force, they are proportional. Assume I have one spring, I show with delta or x deformation. Let's say I show with x. I have this simple one spring. You can remove, you can conduct simple experiment. You can look at to the behavior of the spring inside of the pencil or pen. First step, we wanna apply force and calculate deformation. I apply force 0, deformation is no deformation, it is initial length. Then I increase force to F1, deformation, we will have deformation x1. Then I gradually increase F1, force to the F2 value, so deformation will be x2. I will increase to the F3, deformation will be x3, and so on. If I show those in xy coordinate, what I will have? X coordinate, x-axis, I show with x deformation, y-axis, I name it as a force. If I show these points here, we will have one linear line for linear elastic material or elastic spring or rubber band or something like that. So here you see force and deformation, they are proportional. The slope here, slope, angle is alpha, slope means tangent alpha, is equal to, you see, height, which is F, divided by this length, which is X. This tangent alpha, it is constant number for linear elastic material, and we will show that with K, we call it stiffness of spring. That is right for linear elastic material under proportionality limit stress. We have the same behavior, very similar behavior, if we have bar or rod subjected to axial force in centroid, and if we apply force and we know the length, we know the cross-sectional area, in that case, in each step we are applying force, we can calculate stress, force divided by initial cross-sectional area, and we can define strain as a deformation in each step divided by initial length. And if we draw the stress-strain curve for linear elastic material under proportionality limit stress, or under proportionality limit stress, the relationship is linear. And here, this angle, if it is alpha, tangent alpha, we will show with E, and we call it Young modulus. And from here, Hooke's law, in the material, we can write sigma is equal to E epsilon. Because sigma stress is force divided by cross-sectional area is equal Young modulus times strain is deformation divided by initial length. From here I can write delta is equal PL over EA. So let's now summarize these two behavior in spring and rod. So if we have a spring, we apply force F, deformation I show with X. Hooke's law states F is equal Kx or K. Stiffness constant is equal force divided by deformation. If we have rod made by steel, for example, we apply force under proportionality limit for linear elastic material. I can write sigma is equal E epsilon. This is Hooke's law. And from here, I can write delta deformation is equal to PL over EA, because this is equal to P over A, sigma, or normal stress, and epsilon is equal to deformation over initial length, and L here initial length, and A is cross-sectional area, and E Young modulus. I can write this delta is equal to P over E A over L. It is the same. From here I can write X is equal F over K. Look at here. X is deformation, delta is deformation, F is force, P is force, K is constant, constant number. It is spring stiffness, stiffness of spring. Here EA over L, again we call it axial stiffness. K is spring stiffness. EA over L is axial stiffness for this member, for this axial member. So they have the same behavior. Under axial load, material behaves similar to the one linear spring. So let's refresh your memory about combination of springs. Combination of springs you know, but let's again one more time we will look at together. If we have several springs, how we can attach these springs together? So spring combinations. We can attach a spring like this. We have one spring, stiffness for example it is K1, then I add another spring, stiffness is K2, I add another spring, stiffness is K3, and so on, and I apply force here. In this case we will call it springs in series. Springs in series means there are one spring after another one. If I apply force here, what is happening? This force will transfer to this spring, will transfer to this spring, will transfer to this spring. For example, if we have three springs, internal force in each spring, it is F, F, F. So, if deformation for spring 1, I show with X1. Deformation for spring 2, I show with X2. And deformation for spring 3, I show with x3. Summation of x1 plus x2 plus x3 will be equal to entire total deformation x. So summation of deformation for each spring, if I add together, I will end up with total deformation x here at the end. So if I want to substitute these springs with one spring, that one spring behaves exactly similar to this spring. That will be one equivalent stiffness and one equivalent spring, and the stiffness of that spring we will call it effective stiffness of that equivalent spring. So here, what is the deformation and spring 1? Deformation in spring is equal to force divided by stiffness. So deformation in spring 1, it will be force in spring 1 divided by stiffness of spring 1. So F over K1 plus deformation in spring 2 will be force in spring 2 divided by stiffness of spring 2, F over K2, and deformation in spring 3 will be force in spring 3 divided by stiffness of spring 3. Because all internal force, it is constant, F divided by K1 plus F divided by K2 plus F divided by K3. So summation of these will give us total deformation. Total deformation will be force in that equivalent spring. I want to substitute this spring with one another spring. So K effective for this spring will be F divided by K effective. From here, F will cancel from both sides, and 1 over K effective will be equal 1 over K1 plus 1 over K2 plus 1 over K3 and so on. This is one spring, they are in series. So we attach in series 1 spring, 2 spring, 3 spring and so on. And I apply one force in the end, at the end point. We know K effective for equivalent spring is equal to 1 over K1 plus 1 over K2 plus 1 over K3 and so on. Now let's look at the parallel behavior. So, if springs, they are parallel, so springs in parallel combination. We have 1 spring, we have 2 spring, we have 3 spring, and so on. I show here, for example, 3 spring. I attach all these to one rigid beam, and I prevent rotation of this beam. Let's I show you that this is better. I show like this. I attach all these springs to one rigid beam. This rigid beam can move only in the x direction. It can move in the x direction, but it cannot rotate. And I apply force here, force total F here. So if I pull this rigid beam with force F, this rigid beam will move in the x direction, will move from left to right, but it cannot rotate. I will prevent rotation. Pay attention, if I don't prevent rotation, it will rotate. But if I prevent rotation and I apply force, this will move from left to right. And the deformation for each spring will be equal. So if this is spring 1, K1, K2, K3, what will happen? all of them, for example, this rigid beam will come here. All of them, they will deform as much as x. So x1 will be equal to the x2, will be equal to the x3, that will be equal to the x. But the force, external force, will be divided among these springs. So if the contribution of the first spring is F1, contribution of the second spring is F2, contribution the third spring F3, and so on, F is equal to F1 plus F2 plus F3. So if I want to substitute all this spring with one spring, it behaves exactly same as this spring. What will be? It will be K effective times X is equal to K1X plus K2X plus K3X. The reason all of them X, not X1, X2, X3, because the formation for each one, they are equal, they move together. So deformation for spring 1 is equal to deformation with spring 2 is equal to deformation in spring 3. So K effective times X is equal K1X, K2X, K3X. From here, K effective times X is equal to X, is, if I factor out, K1 plus K2 plus K3. X and X, they will cancel each other from both sides. K effective will be K1 plus K2 plus K3. So if we combine spring together in parallel, means the formation of all those springs should be equal. In that case, the effective stiffness, if I substitute all the spring with one spring, it will be summation of the stiffness of these springs. The reason I review this concept, because we apply the same concept in mechanics of material in order to find deformation, and it will help us to solve a lot of real life problems very fast, and we end up with answer. Later on during example, I will explain and you will see why it is good we learn this method. So let's come back to our axial member and again review. So finally, if we have one axial member, the length for this member is L, Young modulus is E, cross-sectional area is A. I apply force, axial force. Deformation will be equal to P over EA over L. From here, P over delta will be equal to EA over L. We call this stiffness of that rod or bar. This is axial stiffness because we have axial load. We pull it or we push it. We pull it or we push it. We apply tension force or compression force. Axial stiffness for that member for linear elastic material under proportionality limit is equal to E Young modulus times A cross-sectional area divided by length. You should know that. Memorize this. Of course, you don't need to memorize. As an engineer, you should not memorize anything. You should understand and you should be able to prove it. Let's look at to this member. If the direction of the force and member, it is not same direction, what will happen? Assume we have one diagonal member or inclined member, something like this, and I apply force here, P. The length for this member, it is L, cross-sectional area it is A, Young modulus it is E. What will be deformation of this rod or bar in vertical direction? How much this, for example, point B, point A, point B, how much this point B will move down and will come to the point B prime? What is this value? If I can find that value, force divided by deformation in vertical direction will give us the stiffness of this member in the load direction, the stiffness of that member in the load direction. Assume this angle between the member and the line of action of the force, it is alpha. How I can find that? It is easy to find that. How? If I have that member, let's look at to the member behavior. I apply force here, force P. Force P is external force. I apply and it is known. What will be internal force in this member? F. If this angle is alpha, and if I write summation of forces in vertical direction, and I put equal to the 0 in order to equilibrium, I should satisfy this equilibrium equation, I will have F cosine alpha is equal to P. From here, F will be equal to P divided by cosine alpha. So internal force inside of this member will be P divided by cosine alpha. External load divided by cosine alpha. That member, internal force, now we know it. Internal force in that member, which is P over cosine alpha times the length of that member, which is L, divided by EA, will be deformation of that member in member direction. Pay attention. Deformation of that member in the member direction. It means it will be this deformation. So this deformation, axial force in this member times the length of this member divided by EA of this member will be deformation of this member in the member direction. I show with delta. I can calculate that. Everything is here known. Alpha is known, P is known, L is known, E is known, A is known, so I can calculate it. Then, what will happen after this member? Therefore, it should move down. It should come like here, down. So, how it will come down? In order to move down, this member now, it should rotate respect to A. So, L plus delta should rotate respect to A. It means for the center of the A and for the radius of L plus delta, if I draw one arc like this, it will show the location. That arc in small deformation range, will be similar to the tangent to the pathway. Tangent to the pathway, it will be perpendicular to this member. So if deformation is delta, if I draw perpendicular to this deformation delta, in this triangle, this will represent us delta V. So from here, because this angle was alpha, this angle now it is alpha 2. If that angle is alpha, what is happening over there? Over there, you see delta V, vertical deformation, cosine alpha, delta V, cosine alpha should be equal to delta. From here, delta V will be equal to delta divided by cosine alpha. Because I have delta, if I plug here, let's say right here, delta V is equal to delta. Instead of delta, I plug from here. I will write PL over cosine alpha. I rewrite one more time. It will be PL over cosine alpha over EA over cosine alpha will be delta V. What I did, instead of delta, I plug here, you see, delta here is equal to PL cosine alpha EA. So delta V will be equal to PL over cosine alpha divided by EA divided by cosine alpha. That will give us what? That will give us, let's see, this will be equal to P, yes, that I can write, if I rewrite this, I can rewrite this as a PL over EA cosine alpha, and now I can write this PL over EA cosine square alpha. So if I summarize everything, if we have one rod in diagonal direction, I apply force in this direction, and the angle between the member and the line of action of the force is alpha. Deformation in the force direction, force here in vertical direction, deformation in the force direction will be delta V, will be equal to PL over EA cosine square alpha. From here, I can write P over delta V is equal to EA over L cosine square alpha. Force divided by deformation will give us stiffness. Force in here in vertical direction divided by deformation in vertical direction will give us the stiffness of this member in vertical direction. So stiffness of this member in vertical direction always is equal EA divided by L cosine square alpha. E is Young modulus, A cross-sectional area, L is length, cosine square alpha is angle between member and the line of action of the force. Stiffness of this member in the force direction is equal to EA over L cosine square alpha. If I rotate this member and bring to the force direction, what will happen? If I rotate this member and I bring it to the force direction, it means I rotate this clockwise and I bring it to the load direction. I make it alpha is equal to 0. Alpha is equal to 0. What will happen? If I make alpha is equal to 0 from here, K alpha is equal to 0 will be EA over L cosine square 0. What is the cosine 0? Cosine 0 is equal to the 1. Cosine square 0 will be 1. So stiffness will be equal to EA over L. And we know that. We know if we have member and we have force in the axial direction, the stiffness for that member, it is equal to EA over L. For now, it is enough. Review this video, try to understand everything I cover here, digest this material. I will solve several problems and you will see this concept help us a lot. Of course, if we know the concept, we know the assumption, we will know where we should apply. We cannot apply in any location. Our assumption should be right. We know what is our assumption and how it works. We know the concept, and so we can understand in which problem, in which nature of the problem we can apply this concept. And if we apply this concept, you will see for one problem, maybe we need to solve using force method. It will take 1 hour. Using this method, we will solve it in 3 minutes. Thank you so much for watching this lecture. See you next session.